In this video, we're having a look at how we identify some of the key features of this graph. Now we can see that there are some intercepts going through, in this case, the x-axis, and there's another one over here that's off the page. But we'll leave the intercepts for the moment, but they certainly are a key bit of information for the graph. What we're going to look at in this exercise here is the extreme points. So we can see here that we've reached a maximum on the graph, and that's occurred when x is at -4. And we can see here we've got a minimum point at the graph, and that occurs when x is equal to +2. And whilst it's not immediately obvious, somewhere in this region the graph reaches its maximum steepness. So we can see here that the graph is flat at x equals -4. It gradually gets steeper in a negative direction, and somewhere in here it's at its maximum steepness before it starts to reduce the gradient and it starts to flatten out to the point where at this particular stage, x equals 2, the gradient is equal to 0 again. So here's the equation of the graph in question, y equals x cubed plus 3x squared minus 24x. And we're going to have a look at how we use the second derivative to help us identify some of those features we just looked at. First of all, what we'll do is differentiate that equation, and we get the first derivative is y dash equals 3x squared plus 6x minus 24. And then we differentiate that again for the second derivative, and we get 6x plus 6. Now we know that the extreme features of the graph, in other words the turning points, occur where the graph is momentarily with a 0 gradient, or y dash equals 0. So we'll put y dash equals 0 to determine the x value of where those stationary points actually are. And if we go through and solve this is a factorization question where you can solve 2 brackets equal to 0, or you could use a calculator to assist you. We get the solution for y dash equals 0 is such that x equals -4 or 2. Now if we had a graph, we could clearly label which of those values gave us a minimum turning point and which gave us a maximum turning point. But we also needed to be able to determine that without seeing a graph. So what we do is we test it with the second derivative, y double dash. Let's have a look at our graph and see if we can justify the reasoning behind why we use the second derivative to help us. So let's have a look at some of these key bits of information. In this case, we'll look at the first extreme value where it's a maximum. Let's have a look at the gradient. So we'll identify what's happening to the gradient. We can see here that it's a positive gradient and it's gradually reducing until the gradient is 0 at this particular point. So we'll put a positive there, a 0 there, and we can see now that the gradient is negative and becoming more negative as we move to the right. At this particular extreme value where it's a minimum, the gradient is also 0 when x equals 2. And we can also see that the gradient is negative to the left, and the gradient starts to become positive here as the graph increases as we move towards the right. So that means that the gradient is decreasing in this particular region. Now if the gradient is decreasing, that means that y dash is decreasing. And we know from derivatives or rates of change that if something's decreasing, its derivative is negative. So the derivative of the first derivative is the second derivative. So if that first derivative is decreasing, in other words the gradients are decreasing as we move from left to right, that means the second derivative is less than 0. Likewise over here we can see that the gradients are increasing as we move left to right. That means that the derivative is increasing. So there's a positive rate of change. That means the second derivative is greater than 0. So we can now see a connection as to why we have the second derivative to determine the nature of a stationary point. When the second derivative is negative, that means it's a maximum stationary point. If we investigate further where the gradient is 0 and it turns out the second derivative is positive, that means it's a minimum turning point. To assist us to find another feature on the graph, in this case the point of inflection, we can put the second derivative equal to 0. When we solve that, we find that x is equal to -1 in this case, and that means that a point of inflection may occur at x equals -1. Let's investigate further at x equals -1. There's the point on the graph. And at this particular point, we know the second derivative is equal to 0. Now, whilst it's not immediately obvious by looking at the graph, that's the point where the gradient, or the first derivative, is at its extreme. We can see here the gradient is negative, and it's becoming more negative as we move left to right. And at this particular point here, the graph is at its steepest. So the gradient, or derivative, is at its least, the most negative it actually can be in this region. That means the second derivative will equal 0. And this is called a point of inflection. Once we pass this point, as we move left to right, the gradient is gradually increasing to the point where it becomes 0 here, and then becomes positive as we move left to right.